So the agenda here is that I'll start with an introduction of the long-term aim, and then a bit of background about relational frame theory and how it applies to autism and robotics research. And then I'll introduce our initial system and show how we deployed it during a real clinical setting with a child and a therapist, and what lessons we took from that can inform future versions of the robotic system. So I guess a global problem that we're looking to solve is that autism spectrum disorder individuals have deficits in social engagement, which are generally attributed to an underdeveloped theory of mind. So that's our ability to attribute mental states to others and take different perspectives in certain social situations. And then this inability or these deficits can have issues in a wide variety of ways, and there's a variety of clinical interventions that look to develop these perspective-taking capabilities to improve quality of life. So our global solution then is to combine two emerging subfields of autism research, the first being relational frame theory, which a lot of interventions or modern interventions are using as their theoretical basis, the other being robot-enhanced interventions, which again are showing recent promising results in this area. And we're looking to combine the two to reap the benefits of both of them. So relational frame theory is a theory of language and cognition, and it approaches perspective taking as a problem of underdeveloped relational responding. So relational responding is this ability to identify relations between arbitrary stimuli without actually explicitly training those relations. So an underlying skill or an example of a relational skill would be mutual entailment. So deriving the reverse form of a taught relation, or combinatorial entailment, which is one down here, which is combining your knowledge of two known relations to derive a third relation that is, again, it's untaught. And then this applies to perspective taking by focusing, or when we focus on a specific group of relations. So that's deictic relations. And so these are relations that refer to the perspective of others, or are dependent on the other's perspective in a given situation. For example, the left-right relation is dependent on the other person's perspective in an other-oriented interaction. So it's these relationships that depend on other people's perspectives, and that then generalizes to I and you, or here and there, or now and then. Is dependent on the other person. So then these relational respondings, it sort of represents a tangible skill that can be taught to autism individuals to then develop perspective-taking capabilities. So the process would begin with simple relational skills like same or different relations, and then progress to more complex deictic frames that have more direct applicability to perspective-taking. And then the benefit here is that we're teaching underlying mechanisms of perspective taking that generalize across contexts. And in doing so, RFT is addressing some of the criticisms of alternative interventions like operant theory that just use reinforcement techniques and don't generalize beyond the specific social scenarios that they were trained with. So then that other subfield is robot research in autism. And these again have innate benefits of providing a predictable learning partner. They also provide an opportunity to collect data that would otherwise be unattainable. And in terms of the state of the art, there's been a shift towards more autonomous systems, but even these modern systems still use the traditional intervention strategies based on operant theory. And again, with that is carried the same criticisms of not generalizing beyond these specific trained scenarios. Then our general aim here is to combine the benefits of the two emerging subfields and develop a specialised robotic system for RFT. So we start with a basic system that can deliver basic RFT training that we've developed over the summer. We deploy that in an observational study with a child and a therapist, and then we run a thematic analysis that first wants to evaluate the performance of our current system, and second of all to identify additional functionality that could inform the future roles that the robot could take in this kind of context. So a bit about the system, or the development of our system. We formalised the task by saying that we curated a session that the robot could feasibly replicate. And this session trains a very simple relation of same versus different. And in this case, the child will be presented with some animal stimuli, and they would have to derive relations between the animals depending on which foods depending on whether the animals like the same or different foods to the other animals on the trial. So to do this during normal RFT sessions, you need to first clarify that or confirm that the child has necessary prerequisite skills. And here that's the ability to differentiate between objects based on their physical properties. And we do that via two protocols. The first is just to basically spot the odd one out. And the other one is presented with two stimuli and ask the child are the same or different. And so these two protocols is something that the robotic system that we designed can replicate and perform. And then once this is confirmed, we moved on to the relational training. And again, as I mentioned earlier, we're training mutual entailment and combined combinatorial entailment. So we'll say if there's a tiger, a horse and a cat, we'll train that the horse likes the same as the tiger and test mutual entailment by asking who likes the same as the tiger. And then you can see that there are derived relations being formalized in the opposite direction. So to achieve that, we had some baseline functions that the robot needed to have. So first is a vision subsystem, and the robot we're using is a Now robot. It's a humanoid robot that has its own visual system, but we found that wasn't very accurate or sufficiently accurate for the task we needed it to perform. So we trained our own faster RCNN on a customized data set with the stimuli that will actually be used in the actual sessions. And we found that did outperform the baseline on reliability using mean average precision as our performance metric. And so we integrated that into a visual processing system that essentially captures an image with the Now camera, feeds it through the network, and that outputs a list of the stimuli that are present for the given trial. And then the next baseline function is an auditory processing system. And here we just use Now's inbuilt one, which summarizes a response using a trigger word. So, for example, if the child vocalizes, it's the same as their response, this system would understand the response to be the same, and it'll pass that on to another module, which then decides whether the child got it correct or incorrect. And then the last function that I wanted to talk about is the operator interaction capability. So it was quite important to us that the child was receiving reliable teaching methods, and so we didn't want the robot to make mistakes. So whenever the robot wants to evaluate the child's response, it checks in with an on-hand operator by displaying its intended reply on a screen. So, for example, it would display correct, and the on-hand operator, if it thinks it's also correct, will press enter and it will continue. Otherwise, they'll input some kind of correction. And so to see that in action, we can look at this system architecture for one relational training paradigm. The session will begin with the robot introducing the task. The therapist then presents the stimuli. The robot identifies the stimuli that are present with its visual subsystem. It defines the relations for itself, the robot self, by referring to a knowledge base that contains a set of pre-registered relational rules that it can then use to understand for itself how the different stimuli presented relate to each other. And then it teaches the relations to the child. So if you have a cow, a horse, and a cat, it will teach how the three relate to each other. And then it will test the key combinatorial or mutual entailment question to see if the child has derived any new relations from the ones that has been taught. So we'll ask the question, hear the response, evaluate the response according to its knowledge base, and then refer to an on-hand operator to check that it's come to the right summation. That, for example, if it thinks the child is correct, it will check that the operator also thinks that. And then it will deliver some feedback and then go on to continue the session. So we deployed this in an observational study with a child and a therapist with some relational training. And then for this part of the investigation, we present two broad aims. The first is to evaluate the performance of the current system. So how well the auditory and visual system performed, and the other was to identify ways in which future iterations of the robotic system can further assist or enhance the RFT sessions. So the methods here was we recruited a 3.5-year-old boy. We used the Now 6 humanoid robot. During the session, both the therapist and the robot delivered some of the protocols, and then we recorded the entire thing with 3 webcams. And so for evaluating the system, we implemented a self-regulation module where the robotic system would just track how many times the operator had to correct the robot. And we use that as a proxy for the accuracy of both the visual and the auditory sub-processing systems. And then the other side of this is a thematic analysis. Thank you. Where we observe recordings, we identify themes that relate to the therapist's actions or the child's responses to the robot. And from that, we can extract an understanding of how future versions of the robot can help and enhance relational training therapies. So regarding performance, the visual system did pretty well. So you can see here that for only 2 out of the 6 robot responses that relied on the visual system, only 2 out of 6 required the operator's input, which obviously isn't ideal, but it's a bit better than the auditory processing system. But the problem with the vision was that there was an inference latency issue where the child was waiting for the robot to understand the scene and to give a response. And in that time, the child can easily become disengaged. So that's something that we have to address in the next iteration. And then the other side of that is the auditory processing system had a high error rate. So we need another method there, for example, using external microphones, such as that with the Kinect, which is what other research does at the moment. And then the thematic analysis that looks to identify these future roles of the robot and any future modules or capabilities that we can build into it. We identified 3 categories of themes. So the first is around child engagement. So we saw that the therapist was issuing a set of re-engagement techniques when the child became disengaged. And on the reverse of that coin is that the therapist was identifying when the child became disengaged with a set of pretty reliable disengagement behavioural cues. And so from this, a further module could implement something like an engagement detection system that can detect these behavioural cues and then implement those re-engagement strategies. The next theme was around like the fact that this is just a very cognitively demanding task for the therapist. These are intricate protocols that they have to deliver, and in fact the therapist would every now and then ask the wrong question at the wrong time. So having a robot present to deliver these repetitive and predictable procedures could be really valuable to take a bit of pressure on the therapist and allow them to concentrate on other parts of the session, like monitoring the child's progress or their engagement. And then finally is robot-oriented behaviours. So the child expected more animation during the therapist-led procedures. So Charlie's the name of the robot, and at one point it asks, why is it just sitting there? So perhaps having an active listening module would give the impression that the child and the robot were learning from the therapist together. And in that way, the child maybe was less distracted, but also more engaged in what the therapist is saying and the task in hand. I should say from that thematic analysis, I appreciate this is almost anecdotal evidence because we just had one participant, but the aim was less to take any statistical significance from these results. It was more to just get a general understanding of what was required by these relational training protocols and how this can be improved upon in future versions of the robot. So I guess, yeah, to sum up, we're combining 2 emerging subfields of autism research. The first is relational training, and the second is robotic interventions, and we're applying them to try and improve perspective-taking capabilities in children with autism. So in doing this, we present a semi-autonomous system for delivering these basic relational training protocols, and then a subsequent observation of a child and therapist interaction revealed some actionable insights that then we can take going forward into next iterations of the robot, including engagement detection, repetitive procedure delivery, and also a possibility for an active listening module. So yeah, that sort of brings me to the end of the talk. If there's any questions, please do let me know. Hey.
You talked about an active listening module where the robot might interact back in the child's lesson or observation.
Yeah.
Would the aim there be to anthropomorphize the robot more, which you worry about running into the uncanny valley problem? And would there be competitors of that?
So I think the active listening module would be. Oh, sorry. The question was, how would the active listening module be implemented, and are they concerned of running into the uncanny valley if we get it too anthropomorphized? So we'd use the active listening module if the therapist is running a session. So if the therapist is teaching something to the child, then we'll just have the robot do some subtle engagement, like nodding along, just to stop it from just standing still, essentially. I don't think uncanny valley was too much of a concern, just because the robot is, it's a small humanoid-esque robot, but it's not, it doesn't look human-like. It's very much still a robot. So we're not concerned. There may be a concern of like reinforcing robotic traits in the autism child, but I think that may be a separate issue that other research is looking at. Hopefully that answers your question.
Following on from that,
Hey.
Is there even a need for a robot? Is this, there's just a speaker and a camera, or is that not good from a therapeutic point of view?
Yeah, so it's a good question. I think there's two aspects there. First of all, robots are having benefits in the context of autism, so they keep the child engaged, they provide a predictable learning partner, reduce social anxiety. And the other side of that, there's actually an innate value of applying robotics to relational training itself, because if we look at those deictic frames we spoke about earlier, having the robot present as another predictable being from which the child can take the perspective could be a really valuable tool. So, for example, if you're teaching that left-right relation, the robot can raise their right hand and the child can understand that's my left hand from my side of view. So I think robot does have applications to autism research generally, although there's still, I think, a debate there to see how effective they are. But then for our niche goal here, I think there is like inherent value in having the robot present.
Any more questions? Is there any questions?
No, that's no question.
Anybody else? Yeah, come.
So you mentioned the latency issue of the robot. Have you got any ideas of how you might address that? Would that be looking at changing the models or changing the hardware or combination?
Yeah. So the question is how we're going to address the inference latency issues that I mentioned. So at the moment we're using a faster RCNN, which is still quite slow, and we can use other object detection networks like the YOLO V4 or V5, which are far faster. The main issue was that we were running with the Now robot from a laptop that didn't have a GPU. And the thing that stopped us from implementing faster networks was just that there was an incompatibility between what the robot package required and what our Python packages required. So it's something that we'll just explore, but it certainly feels like implementing a new model, a faster model, can definitely achieve real-time object detection. It's just a way of making it match up with the robot.